Good morning, everyone, and welcome back to Foundations of Algorithms. It's lovely to see you again, especially as we're getting to the pointy end of semester, and I see so many faces here today, and that's great for what we're going to be doing today, which is expanding a little more on our tree data structures, moving along to think about how they might influence some of the more sophisticated algorithms that we can run, and then perhaps start to look at combining all the different pieces about algorithms that we have learned so far. Now, for today's history snippet on the board here, does anyone know who this is? We have half a hand from Vincent. We have Lottie. Who is this?
Her name's Grace Hopper, and she was working, I think she was working with like the US Army or something, but she kind of invented the first programming language.
So that's really good. This is not just Grace Hopper. This is Commodore Grace Hopper of the US Navy. She was a rear admiral. She was born in 1906 and died in 1992. And she was really responsible for the creation of machine-independent programming languages. So Lottie was very much on the ball there. Up until Grace Hopper, most of the programming languages were specific to the particular design of the architecture of the machine that was being programmed. So let's say you had a machine called like a PDP-9 or a machine called a Colossus. The way you'd program those machines would be based on the design of that particular machine. It would have its own instructions. But one of Grace Hopper's big ideas was that, you know what, the right way to do this is not for the programmer to have to worry about the particular design of the machine on which they're coding. Instead, it would be much more convenient and sensible if we could abstract away the architecture of that computer and instead have a compiler that would convert a common programming language down into the machine language for that specific architecture. And indeed, this is what our compilers do today. If you write a C program, you don't have to worry about the particular CPU inside your computer, whether it's an Intel or an AMD, whether it's running what we call the x64 instruction set, or if it's running an ARM instruction set, which is another set of instructions that a computer could use. All of that is hidden from you. In fact, if you followed not a word of what I just said in the last 20 seconds, it wouldn't matter because of Grace Hopper, who allowed us to abstract away some of those details and allow us to program in a language that's much more comfortable and also that it is independent and allows us to transport our code across different kinds of computers. She also did much of the heavy intellectual work that actually led to the creation of compilers themselves, as is necessary if you are one of the inventors of programming languages. So the two kind of go hand in hand. And indeed, if later on in your computer science careers, you take an interest in programming languages, one of the first classes that you often take is a class in compilers, so that you can learn both to design your own programming language, but also to write the compiler that will convert what you write in your programming language down into machine code that can actually be executed on a given computer. One fun thing about Grace Hopper is she was adamant throughout her entire life that one day computers would be programmed in English. And now with the rise of things like large language models, we're getting perhaps a little closer to that dream, although the extent to which LLMs are actually programming is somewhat in dispute. The other thing that I'll note here is that she was the creator of the A programming language. And in this class we are learning C, yes, and indeed there is a D programming language and an F programming language. I'm not sure about E actually, but these programming languages are all inspired by each other, and then the other programming language that she's notable for having a very heavy hand in is COBOL, which is still in use today. So if any of you have been following the news about like Doge in the United States and going into different agencies and rewriting all their code, one of the things that they're attempting to do, and I won't say whether they're doing it well or poorly, but replacing some mainframe computers, singular, very large computers running code in COBOL, this very old programming language, and trying to modernize it. Now, that's a very difficult task, and so I think that the jury is out on whether they'll have any success there at all. So taking us back to where we were last week, I want to do a bit of a recap about our tree data structures so that we can then revisit heaps. And remember, we were using trees as a way of, as our like high-level data structure, and then we were thinking about binary trees, binary search trees, and then max heaps and min heaps, all of which are different ways to take the notion of a tree, so having nodes that have children and span out like a tree visual, into different types of data structures that allow us to run algorithms that have different efficiencies. So if you'll remember, this was our opening problem from last week. Which of my descendants lived to 13? And we had an array of structs that we were using to kind of represent these. So what we did was we said, well, one way to handle this problem is we could sort the entire array of structs and then do binary search. Now that gave us an n log n runtime because the sorting was the dominant factor there. We couldn't actually do the log n binary search until we'd already done the sorting. And then if we remove if we remove an element, we're still going to have a difficult time going through the array to remove that element. It's still going to incur a substantial runtime penalty. So this led to our design of a binary search tree. And remember, we had our ape tree. And we had the ages associated with them as the key that we used to distinguish between nodes. So what we'd do is we would try and search based on the ages and then retrieve their name from the struct that was accompanying their age. So if we wanted to find the oldest ape, what we could do is we start at the root of the tree. Now remember, in algorithms, we tend to represent our trees with the root at the top. That's the node with no parents. So we start at the root, and then, wait, this isn't working. This isn't going to get us our oldest ape at all. Okay, this doesn't seem to be in order. All we're doing is going through every single node. This isn't actually giving us any time saving. So going up, going along, backtracking when I run out of places I can go, that wasn't helpful. So what we had instead was we had a binary search tree, which remember had the property that the right child is greater than or equal to the parent, which was greater than the left child. And by doing this, we'd get a different arrangement of our items, which actually made our search operation very efficient. So here, if we start at the root, this time if we're searching for the oldest ape, we can do it much more efficiently. So now we just go to the right and go to the right again. We can't go right any further. There's no right child. And so we have found the oldest ape. What about if we want to find an ape with a specific value? We can follow a very similar pattern, and you'll remember from last week the way we do this is by comparing the target value to the value that we're currently looking at. So we're looking at the root here. We're looking at 20. Is 22 bigger than or equal to 20? Yes, that means we go to the right. So we go to the right. Is 22 bigger than or equal to 33? No, it's smaller, so we go to the left. Oh, and now we have found it. So this then led to our discussion about if we wanted to find the largest item or the smallest item repeatedly. And you'll remember that depending on whether it was going to be the largest item that we wanted or the smallest item, we'd choose a slightly different data structure, either a max heap or a min heap. And the property here was a little different from binary search trees. Instead of requiring this strict ordering property between the left child, the parent, and the right child, we just said that everything in the subtree should be larger or smaller depending on whether we're a max heap or a min heap. So for a max heap, the parent had to be larger than all the descendants, and for a min heap, the parent had to be smaller than all the descendants. And this is where today's adventure is going to begin. So you'll remember from last time, we looked a little bit at the Sift-Down operation, and I said this was going to be the key operation that we would use to build up our data structure. And so now we're going to take a look at actually doing this with an example. Here we go. Here is our array thus far. We're just representing it using a tree visualization, but this is just a collection of elements like we had before. And so now what we're going to do is we're going to perform the Sift-Down operation repeatedly. You'll remember the Sift-Down operation. Let's do an example of it quickly let's start in this case. So now let's pick the 2, which is the last non-leaf. And a leaf is a node with no children. So this is a leaf, that's a leaf, that's a leaf, that's a leaf. Here we're doing the same thing, I've just arranged our tree slightly differently. So let's pick the last non-leaf, which is our 2 over here. And is it greater than the 8? No, it's not greater than the 8. So we swap it up. And let's delete that now. Because now we're going to move on with our tree. So we have swapped the 8 and the 2. And now we move on to the next non-leaf element, which really we know that none of the prior elements now are going to be leaves because we've already excluded all the leaves so far. So the next one for us to look at is this 6 over here. Now, is the 6 larger than the 3 and the 1? Yeah, so we don't need to do any swaps. So moving on again, we now have the 5, which is our next non-leaf element. Okay, so let's do Sift-Down. Is 5 bigger than both of its children?
No.
No. Tim, you're having an off day today. So the 5 is smaller than the 8, and so let's look at the 2 children. Of the 2 children, the 8 is larger, so let's swap that. Okay, so now we only have one non-leaf node left to look at, and that's the root over here. Now, is the 7 larger than both 8 and 6? No. You guys are doing good at the grade school math today. Okay, so we're going to swap it with the largest of its 2 children. And now let's look at our overall structure. All we've done is this sift-down process over and over. But now let's look. Is 8 larger than all of its descendants? Yeah, it seems to be the case. Is the 7 larger than all of its descendants? Yes, the 6 is larger than all of its descendants. The 5 is larger than all of its descendants. And the rest are just leaves, so they have no descendants. And so what we've actually done by applying the sift-down operation repeatedly on all the non-leaf nodes is we've managed to actually construct a heap. So now we have a complete max heap. So what we can do is if I wanted to get the maximum value of all the elements really quickly, I could just look at the root. And so now in an O of 1 step, after I've constructed the heap, I can get my maximum. But what we probably want to do is, I said what we're going to want to do is use this for a queue. Remember last time we were distributing the Taylor Swift tickets based on grades. And if we only get the same maximum over and over, that's a queue that never moves. And we really want to get the first person out of the queue and move successively on to the next people. So what we're going to want to do is a series of successive remove maxes. And so that is going to be our pop operation here. The way we'll do that is as follows. We are going to swap the item that we want to remove to the last position in the tree. So that 2 over there was in the last position. So swap the root with the 2. And now our 8 is very easy to remove. But we have a problem. What's the problem now?
There's still one pointer pointing to some deleted element.
Okay, so we're not using pointers in this example. We're doing this one with arrays. Garv has, let's get Garv a microphone. Or Lottie, do you still have it? Yeah, let's give that to Garv.
It's not a max heap anymore.
It's not a max heap anymore. Give me some more specific details.
The children of 2 are larger than 2.
Yes, so 2 is all messed up now. Now, if I want to put 2 in the correct place in the heap, what can I do? We only have learned one operation to do with our heaps so far.
You can do a bunch more sift downs to get it.
So let's do the sift down again. Now, 8 is no longer part of our heap because we actually wanted to remove it. So let's do sift down on 2. So is 2 greater than its descendants, than its children? No, so pick the larger of its 2 descendants. Garv, tell me what to swap.
Sorry, I keep turning the mic off. Swap it with 7.
Swap it with the 7. Okay, am I done? Is 2 larger than its children? Okay, so what do I do?
Swap it with a 5.
Swap it with the 5. And do I have a max heap again? So now I have a max heap again, and I've removed a single element. So how about we do this process again? Do you think you can help me out with that?
Sure.
Okay, so let's say I wanted to remove max again. Well, what do I do?
Well, 8 is gone now, so you swap the 2 and the 7.
Well, what is the last node? If I were to write this out as an array, my array would look like 7, 5, 6, 2, 4, 3, 1. So what's the last element?
Swap with the 1.
Swap with the 1. So let me remove that temporary array that I made, just for illustration. So we are going to swap our 7 with the 1 here. Okay, and now I can remove the 7 from consideration. But what's the problem?
Not a max heap anymore, so the 1 is not larger than its descendant, so you have to swap it with the 6.
Okay, so swap it with the 6. Am I done?
Nope, still not large, so you got to swap with the 3.
Okay, so swap it with the 3. Now am I done? Okay. So that's good. Now I've given a ticket to 8 and 7. Let's make sure that everyone gets a ticket. So who's the next person that I remove?
Well, you're removing 6, and the last one in the array, I think, is 1.
It's still that 1 that's getting swapped back up. So we're going to do that swap, remove the biggest item, and the way we remove it is by putting it at the end of our structure. And remember, one by one, we're eliminating these items from the structure. But when we're using an array, what we can do to figure out which items we've eliminated is just, when we're counting how large the array is, let's just reduce our count of how many items are in the array by 1. And we'll come back to that in a minute and you'll see why. So essentially, our array is going to look something like 1, 5, 3, 2, 4, 6, 7, 8. And those of you who are particularly astute might notice something kind of interesting going on here. So I'm going to leave that 6, 7, and 8 there for the minute. What's the problem, Garv?
Not a max heap.
Not a max heap. What do we do?
So you swap it with the larger of the descendants. And
Swap what with the larger of descendants?
swap the root with
Yep.
the larger descendant, so you swap 1 and 5.
1 and 5. Are we done?
Nope. So you swap again 1 and 4.
Okay, but now I want to give 5 a ticket.
So take out 5, swap it with the 1 because it's still the last one.
Okay, and now I'll draw a blue line there just to indicate that it's eliminated. And in fact, I will write down what's happening in our array. Okay, are we fine?
No, not a max heap. So swap the root with the larger of the descendants again. So 1 and 4. And still not done, so swap the 1 and 2.
Okay, all good. But now I want to give a ticket to the number 4.
So you continue, you swap with the last element, so you swap the 4 and the 1. Unconsider the 4. And then you swap the 1 and the 3.
And?
Now we want to get rid of the 3. So we swap the 1 and the 3 again. Stop considering the 3. Write it down at the bottom. And not a max heap anymore, so we swap the 1 and the 2.
And?
We're like, okay, we want the 2 to get rid of the 2, so we swap the 1 and the 2. Stop considering the 2. Write it down at the bottom. And now we just have the root node left, so we have a max heap.
But we should probably give the last person in the class a Taylor Swift ticket. We don't want them to be out on the cold watching all 500 of their classmates have a good time. So let's write down the 1 as well. And now look at what has happened to our array.
It's being sorted.
It's been sorted. So what we've actually done here is we have discovered heap sort, which is essentially just this idea of take your elements, put them in a heap, and then one by one remove them, except instead of like removing them from the computer's memory entirely, all we're going to do is just say, okay, those elements have already been considered, don't consider them for the rest of the algorithm. So take them out of our heap, but leave them in the array. And then when we come back and look at the array, our overall array is sorted. So that is a wonderful kind of intuitive explanation of the heap sort algorithm. And you can see it that there are 1 or 2 instances in which there are swaps which you might think are unnecessary. But the reason we're doing them is so that we can actually maintain this heap structure to allow us to continue on with the algorithm and ensure that the whole thing has a total and correct ordering by the end. So we'll go to Garv's question and then to Tim.
Does that make quicksort better? Because it seems like quicksort only does like necessary swaps, while this did a couple unnecessary ones.
So we'll go to the runtime analysis of this soon, but we'll also discuss a little bit about the practical runtime of some of quicksort versus heap sort, and there'll be some interesting things there which actually change which algorithm we might end up using, but hold tight on that one. Tim?
So my question was, the advantage of this is that when you're taking it out, say if you already had like a sorted, a normal array, and it was sorted, and you just wanted to take out the first element. Well, taking out the last element would be easy, but say it was reverse order and you wanted to take out the first element and then bring everything else forward, that would take O of n, because you have to move everything, whereas with this, the advantage is you only have to move far fewer elements when you pop.
Yeah, that's exactly what's going on here. And we're about to do the runtime analysis to really dig into that and figure out how much time are we actually saving. But Tim's got the intuition right in that removing is a relatively cheap operation. It involves one swap and then a Sift-Down. And the maximum that Sift-Down can take is the height of the tree because you can only swap it down so many levels. So our Sift-Down runs in log n time because log n is going to be the height of the tree. But the other thing to note is as we start locking off parts of the tree, the height is going to become smaller. So it's not really log n, it's log n in a fashion where we have to consider that that n is kind of changing as we consider a smaller and smaller heap, and that's going to impact the runtime analysis. So we will look at that in a few different ways, both by looking at an evaluation of the code, and then we'll do our usual small bit of maths to actually try and boil that down, particularly where there is recursion or repeated addition at different levels involved. So let's look at that now. And that was a beautiful transition from you two discussing just the issues that we needed to consider next. So here is a representation of our code for build heap and Sift-Down. And Sift-Down is going to be h of I work, where hi is the height of the tree from which you are sifting down. Now our build heap, let's take a look at the loop there. The loop there is going to run n on 2 minus 1 times. The reason why, if we look at the bounds, you might see, oh, that's n minus 2 on 2, not n on 2 minus 1. The reason why we're doing it that way is because if you'll remember in the C programming language, integer division is going to automatically truncate. So build heap runs Sift-Down n on 2 minus 1 times, and Sift-Down is going to be dependent on the height of the tree at that point. Because as we're constructing the tree, like if you imagine inserting the very first element into the heap, it's the root, so there's no further sifting down it can go. If you're inserting a new root and there are already 2 children below, well, you can go down 1 level. So as we add more and more items to our heap, we are going to incur a greater cost to sift down. So let's actually do that analysis. And the way it's going to work as follows. So let's just, in terms of our counting, let the bottom of the heap be level 0, just for the purpose of our counting here, and n nodes total in our tree once we have filled it out. N nodes total in our heap once we have filled it out. So it's very easy to see that if there's 1 node at the first level and 2 nodes at the second level and 4 nodes at the third level, etc., there are going to be 2 to the h nodes at the last level because each level has double the number of nodes from the level prior. So 2 times 2 times 2 times 2 times 2, up to the height of the tree, that's just 2 to the h. Which means we can make the following statement. N is going to be larger than 2 to the h, which is also going to be bounded by 2 to the h plus 1 minus 1. Now the reason is if you figure out the sum of the nodes at the final level, that's going to give you 2 to the h, and the total number of nodes in the entire heap is definitely going to be larger than just the nodes at the prior level. However, if you do 2 to the h plus 1, you're doubling that entire amount of all the nodes at the last level again, which is going to give you an upper bound on n as well. So now we have this nice bound for n sits between 2 to the h and 2 to the h plus 1 minus 1. Greater than or equal to for each of those. So we can say that at level I, there are also going to be a maximum of 2 to the h minus I, and this accounts for the fact that maybe we haven't completely filled out that last level. So if we have, for example, only 2 nodes in our tree, that is the root and 1 of its children. So at that second level, we don't yet have 2 children, which would be 2 to the h minus I. that would only be one parent and then one child. But as we fill it out and as we balance our tree, we're going to get closer and closer to 2h minus I. And the reason we've got the minus I here is just because we're counting from the bottom level going backwards. Which means that for a given node that's being inserted, there are a maximum of I swaps down that can happen. The tree has a maximum height of h. The bottom layer is layer 0, which means when we're at the top, we're at h, which means there we can do a maximum of h swaps down. So starting at the hth level, which is the root, we can go down to h minus 1, h minus 2, h minus 3, all the way until we get back down to level 0, which we defined as being the bottom layer of the tree. So a maximum of I swaps when we're on the ith level. And so if we're trying to figure out how many swaps are happening in total, we can write it as follows. So there are 2 to the h minus I, maximum of 2 to the h minus I nodes at a given level. And for each of those nodes, we're going to call Sift-Down. And the Sift-Down is going to take a maximum of I swaps. That's just combining these two statements from the top here. And then we have to sum this across all the different levels. So we've got h levels. For each level, count how many swaps can be done for each node at that level and sum it up for each of those nodes. So that gives us that expression there. And what this expression is, it's just counting the total number of swaps down that's going to happen throughout our entire construction process for our heap. So now we do a little bit of first year uni maths, or even a bit simpler than that. We get as follows. So take our expression and just break up 2 to the h minus I into 2 to the h divided by 2 to the I. Now 2 to the h here is a constant. The value h isn't changing as we perform this addition, so we can take it out the front. So this gives us 2 to the h times the sum of the expression in there, which is going to be I on 2 to the I. And we can solve this out. That just gives us 2 by 2 to the h, which is the same as 2 to the h plus 1. We also have our bound that we developed earlier, giving a relationship between n, the total number of nodes that are going to be in our completed heap, and 2 to the h. Let's go right back to that for a second. We have this expression here, which we proved earlier. So we know that n is at least 2 to the h, which implies that 2 to the h plus 1 is less than 2 to the n. And so on our last slide, we had 2 to the h plus 1, which now gives us a bound for that. 2 to the h plus 1 is less than 2n. So therefore, the overall number of swaps that we're going to have in the worst case in our algorithm is going to be bounded by O of n. And what this gives us, let's rewind a little bit. What we were doing with this whole repeated swaps thing, counting up every level, we were constructing a heap out of a set of elements. And so what we have finally is that our algorithm for heap construction runs in O of n, which is great news for us because often we've found when constructing some of our more complicated data structures is they actually took a considerable amount of time to build. Here we have a beautiful O of n runtime for our build heap. Do you have any questions about this derivation or about heap construction so far? Okay. So this now gives us all the tools we need to actually analyze heap sort. And now I'm going to show you the code for heap sort, which is very simple. Build the heap, and then just do this process that Garv had us doing. So swap the root element with the last element, and then sift down, excluding that last element, which is now in its final position. So build heap, how long did we just say that it runs in? Chia, you awake? How long did we say build heap runs in? O of n, yeah, we just said it. So it runs in O of n. So that first line over there is O of n. It says it on the board. And then we know that we are running this loop and O of n times. I'm going to ignore the n minus 1 there. Then we are doing swap, which just takes one operation, and then sift down, and we know that sift down runs in log n time. So we're doing n times log n, which gives us n log n. So if we have O of n and n log n, which of those two terms dominates? Is n bigger or is n log n bigger? N log n is bigger, which gives us the final runtime for heap sort of n log n worst case. Now this is really exciting. You don't seem as excited as I am. This is really exciting because our last, all our sorting algorithms thus far, what was their worst case running time? N squared. So this gives us a substantial worst case runtime benefit. So the question we want to ask now, and I will tell you this for a fact, that mostly we don't use heap sort. Say again?
It'd create a lot of heap allocations.
Heap allocations? Yeah, we're kind of close, but except we're doing this in an array. You're all on
Because
track, but there's
they're
something
in
interesting
factorial
going on with memory here. So Daniel, let's take a look at, oh, this was on my iPad, so let's swap it there. Give me a second. And which elements am I swapping in each step?
The bottom ones.
We're going to want to take out the root, and what do we swap the root with? Which element? The last one.
I don't remember.
And then what we do is we mark it as already having been handled. Now, what do we know about the gap in memory between the first element and the last element? It's pretty big, which means that our computer's temporary memory that it uses to handle chunks of items at a singular time might be too small to actually handle both the chunk of memory that has the first element and the chunk of memory that has the last element easily at the same time. And so every time you're doing one of these swaps, what you're actually doing is if your array that you're sorting is really big, you're going to be requesting chunks from all across the computer from that large array. You're going to be requesting chunks all across that array at different times. Now, if we think about something like quicksort and insertion sort, they were always working on elements that are very close together in the arrays, which means that computers that anticipate that we're generally going to be accessing elements that are close together can do that very efficiently. And the way this actually works underneath the computer is dependent on something we call computer architecture, which is the actual design of internally how the computer handles different chunks of memory and how it handles the CPU. So heap sort is going to be asking for items that are very far apart in the computer's memory, and what it's going to have to do constantly is fetch both of those parts into its fast memory at the same time from wherever the slower memory where the whole data structure is stored. And what this means is that heap sort in practice is actually going to be very slow, not because of its formal behavior when we abstract away the details of the computer, but because of its applied behavior. Now, if you're being very perspicacious, you might say, well, that's actually a problem with our model of computation. And that's a fun phrase because that is William over there's class that he teaches. But one of the things that his class actually ignores is a lot of these lower level details, which are important for having a correct model of your algorithm that actually represents its behavior on a real machine. What you'll learn in your theory class, which is models of computation, is something that abstracts away more of these details and does analysis on a computer in an abstracted fashion, but there is always this gap. Now, it can be solved. You can create a model of computation that includes things like the organization of the computer's memory, but often we do away with that because it makes the analysis much, much more complicated. One of the very exciting things for me personally about computer science is the existence of this gap and attempts to remedy it. And that's where a lot of active research can be found, because there are open questions still about how to analyze algorithms, not just at the level where we abstract everything away, but peeling off layers of the onion piece by piece and trying to see, okay, now let's model it a little bit more realistically compared to a computer. Now let's take that away and model it in a universe where the laws of physics are slightly different. Okay, now let's model it where we're building a quantum computer. And each of those lead to different analyses, different questions, and different behavior on real-world problems. And that is why what you're learning in the class is not just useful from a going out and building today, and not just useful from a highfalutin theory perspective, but as a way to think about how we actually merge the two. And so this pathology with heap sort lets us talk about what happens if our data set gets really large. because if the array that we're sorting is only 6 elements, not only will the big O runtime not matter because it'll be pretty fast, but we're not going to run into, in a practical level, like if your algorithm runs before you can blink your eyes, you probably don't care about the big O behavior. But in another sense, if the array is small, we're not going to run into problems around the computer's memory. We could ask again, okay, now let's say, haha, you found an algorithm that can run efficiently inside your computer's memory. We'll use quicksort instead of heap sort. We'll get around that problem you were talking about. But now let's give that sneaky person who thinks they're so smart an array that's really, really large, larger than the whole computer's memory. So does anyone remember we talked about this earlier in semester, what happens when the amount of data that our computer needs is larger than our computer's RAM? Daniel, you've still got the microphone. We'll give you another chance.
It goes into swap memory.
It goes into what we call swap memory, which means that on the hard drive, you can store the entire array. But in your computer's RAM, where you're running the algorithm, you need to constantly be bringing in chunks from the hard drive into your computer's main memory, and then you put some of what's in its main memory back on the hard drive, and then when you need the next chunk, you get it from the hard drive and put it in the main memory. And that slows down the computer really, really substantially. So if we're going to have this problem with a really big array, what might we do if our single computer, Daniel, doesn't have enough RAM, doesn't have enough temporary memory to store the array that we want to be operating on? What might we do? Think creatively. There's not enough memory in our one computer.
You'd use multiple computers.
Okay, give me a little more.
Maybe like parallelize the work.
Explain that a bit. You're getting there. Just more full sentences.
Separate the array into multiple arrays and give each computer one of them. And then like once they're all done sorting their bit, you can combine them into one big array.
And what word might you use for combining? Well, give me a couple synonyms.
Join, merge.
Voila, that is the word we are looking for. So we are about to start our discussion of merge sort, which is particularly useful in this instance because the core technique here is going to be split up your array into let's say for the time being, 2 sub arrays, sort each of those, and then when they're sorted, what are we going to do? Daniel? It's in the name. We're going to merge them. So our operations here are going to be split and join, or split and merge in this case. And this is part of a strategy, a general problem-solving strategy in computer science known as divide and conquer. So if the original problem size is too big for you to handle, split it up into smaller pieces. Can you solve those smaller pieces? If not, what do? Mal's got it. Even smaller pieces, smaller pieces, smaller pieces. Okay, Mal, do you know how to sort one item?
It's just a 0. We don't need to solve it.
Okay, do you know how to sort 2 items? But then Daniel is going to have to help us out with how to merge them. Unfortunately, it's probably a little tricky to do on your own, so we'll do it as a class. The core idea at merge sort is just this, which you were able to come up with intuitively, which is split up the work, so half the items fit in each chunk, and let's say that our array is almost double a single computer's RAM, so we can split it up into 2 computers, have them deal with those chunks, and then join the chunks back together. Now, before we actually get to the full merge sort algorithm, I want to take us on a bit of a detour to actually figuring out how in C we can store the array if it's getting too large for our computer's memory. Because at the end of the day, when we've finished our sorted array, we still want to be able to store it on one computer. Just saying, oh, split it up is not going to be the solution because at some point it needs to come back to one place. And so we need to have a mechanism for our C programs to operate not only in the computer's temporary memory, in the RAM, but also on the hard drive. So we're going to do a short look at some of the C functions that we can actually use to write things to the hard drive. So can we have a drum roll? And here are our new functions: fopen, fclose, fread, and fwrite. Thank you very much. And so these functions we are going to use from inside our C program to access files on the file system, which is another way of saying the organization of things on the hard drive. Now, one nice thing about this interface, these set of functions, is that in operating systems that are derived from Unix, so that includes Mac, that includes Linux, and even now Windows is letting you do more of this kind of thing. The core idea is that everything is a file. So there is some file on the computer that if you were to open it up, has everything inside the computer's memory. That one isn't actually stored on the hard drive. That's a fake file that represents the computer's RAM. If you want to send something over the network, your network card, the little chip in the computer that sends things out, is also a file. So you can open that, read stuff from the network, or you could write to it and write stuff to the network as well. And this is a really cool thing that once you have these few functions, you can actually perform a whole bunch of operations on the system just by using this kind of Unix philosophy where everything is a file. So you can even change settings on your computer by writing to specific files. However, if you were to open a file that contains the contents of the computer's memory, it wouldn't read like a normal text file. It's not going to be readable to you in the way that you'd read like a document that lays out your report card, for example. The difference here is that some files are going to be written in a binary format, that is a format that is ultimately has some kind of encoding, which is meant to be machine readable, versus a text file which is only going to use ASCII characters. So if we think back, ASCII had a limited set of values that could be represented and that actually mapped to characters, whereas binary has the full set of values available to it because that can be interpreted abstractly by the computer. But back to talking about our file operations in C, our fopen, fclose, fread, fwrite, all of these are going to operate on a special kind of structure that represents a file, or hopefully an open file, on our computer. And this is going to be the following file struct, and we're using a file star here because remember, we don't want to pass around the entire struct every time. Much more simple to have a pointer to the struct, and that makes our code more efficient. And if we actually dig into a modern operating system, this is what the file struct actually looks like. So it tells us how many characters are available, it tells us where we can read from, tells us whether it's open or closed, and it also has a special number, this underscore file associated with it, which is a number that internally the operating system uses to match files that are open in your program to files that are actually open on the operating system. Now, the good thing about C is that using a file struct along with the file functions hides all of those details away from us. We don't actually need to know what's inside the file struct. You've seen this once, now you can probably forget about it for a good chunk of your next few years. But it's good to know how it's actually working under the hood, being able to peel open the layers of abstraction and see what's actually going on. Now, there are 3 file descriptors, these numbers that tell us how the file actually matches something on the file system, that are in common to any program when that program starts running. And these start open, so you don't need to specially open them, and these are the following 3. std in, standard in, which is always number 0, standard out, which is 1, and standard error, which is 2. And you can choose when you are performing one of the operations, which of these streams that you want to write to. So, well, we're not going to write to the input, that doesn't make much sense, but we might read from the input. And when we write something, we could choose whether it's an error message or an output message. And the reason we do this is because the output messages might be the results from the program, and the error messages are more of a log of what's been happening. And so you can say to your program, okay, I want you to when the program's finished running, take everything from standard out and put it in one file called results, and then have another file called program.log where I can later go and see what happened. So I can compare those 2 things, and I don't get all of those messages in one stream and have to separate them out. And you can imagine ways in which that might be useful. Now, this also lets us understand a little bit more about 2 functions that we've been using the whole time from the very first week of class. And these are printf and scanf. If you look at the way that printf and scanf are actually written, they're very, very short functions. What printf does is it calls another function, fprintf, which says do printf, but do it to standard out. Just whatever the user said that they wanted to print it, but on standard out. And scanf is really fscanf standard in, because these underlying functions, fprintf and fscanf, allow us to read and write from different file descriptors. So for example, you could use fprintf and do formatted printing to a file that you've opened that's not standard output. Now, when I said printf is simple, what I mean is that printf itself is not too complicated. fprintf is really complicated. And the reason for that is all the logic needed to do the fancy formatting. Tim, you have a question.
So this whole time, when we've been doing these functions, there's actually been files that are hiding that we can't normally see. Like if you're in the File Explorer, you can't see this standard input or standard output or standard error, but you're saying they're there. They're in the memory. Is it in the same folder as the file? Like, where are these files?
So if you're on most Linux distributions, if you go to the root of your file system, so you've seen, like, if you click on a Mac, you'll see like Macintosh hard drive. On a Windows, you'll see C drive. On Linux, it's just /, that's the name of the directory. Under there is a directory called /proc. Under that directory, there is one folder for every open program on the computer. In that directory, you'll actually find normally 3 files named 0, 1, and 2, which are going to be these equivalent streams. So you can actually find those files directly, but manipulating them is an interesting task.
So this is not unique to C?
This is not unique to C. This is about the design of the operating system. And it's part of what we call the POSIX standard, which is a set of design documents which say, okay, one philosophy by which you could design the computer is by having everything be a file at some level of abstraction. Now, underneath that, the way that those files work is determined by the operating system. So in truth, they are actually writing something. It's not really a file on your hard drive, but they're still represented as files somewhere. And I found it fun when I was an undergraduate to like explore some of these weird directories on a Linux machine and figure out what they do. Okay, so we've got our open function, our read function, our write function, our close function, but we need to also know one more thing about the arguments they take, or 2 more things about the arguments they take in order to actually use them. And these are the different modes by which we can open a file. So we have to tell the operating system, what are we going to do once the file is open? One thing we can do is open the file for writing. Now careful, opening a file for writing means treat the file as a new file. So this will overwrite anything that was in the file before. So if you open a file in W mode, it will delete everything there. Be very careful with this. If you open it in R mode, it allows you to read from it. And then if you open it in A mode, this will allow you to do the write, but only append to it. So not only append to it, it will allow you to append to it. So this is a mode which doesn't overwrite everything that was in it before. And then there's also some functions where we won't talk much about these, but fseek and ftell, which allow you to jump to different points in the file rather than reading and writing sequentially. And so these have an extra plus that you can add, which allows you to jump about. Now, one other thing is you can also add a B when you're telling the computer how you want to open the file, to say that this is not going to be an ASCII file, this is going to be a binary file. And
So add B to the... So the B is as a, hang on, wait. So we add B to, when it says flags, that just mean as in the sense, the other previous mode, in the same way as the other previous mode. Okay.
so let's make this a string. And
Another statement, like if I look at the man page for a verb,
okay. Now we're also going to need a char to a string to hold our file name. So let's call this hello.txt. And now the way that fopen works is with the file name, which should be a, made a mistake there, which should be a string. And then the mode that we're running, that we are opening it to, the mode in which we are opening it as a string as well. Vincent.
Hang on. Are the double quotes supposed to be there for the mode?
For which?
The W for the mode.
Yes. So that is as a string rather than as a character, I think. Otherwise, you wouldn't be able to write like WB or RW. You wouldn't be able to open it in a joint mode. Yeah, if it only took in a character. Okay. So what we also want to do is, because the file system is a place where natural errors might occur, so your hard drive might be full or a file might not exist, here we always want to be pretty careful about making sure to check the outcome. So called it my file. So what we're doing here is a trick to do two things at once. What we're doing here, the first thing that we're doing is we're setting my file to be the result of fopen, and then at the same time, we're simultaneously checking if it's non-null. So if it's null, and then for this, we're going to need the standard library as well. Then let's fprintf to my file. We go to the man page. I typed in to get to this man fprintf. And so we can actually look up and see what the function signature is. So fprintf takes in a file star pointer, and then it takes in the normal printf arguments. So if you're confused about what const char star restrict format is, we can just look and see that it's actually the same set of arguments as printf, so we don't have to worry there. So my file, then let's write a string, and what the string will be hello.
Use wrong, yeah.
There we go. Thank you. Now let's do fclose. On my file, it's always good behavior to close things after you've opened them. The only thing to note here is that if you don't close it, it's kind of the same way that malloc works. When the program ends, the operating system will forcibly close the open files. And I've accidentally created this in lecture 8 instead of lecture 10. Okay, let's compile it. And run it. Now, assuming I've made no mistakes, we have hello.txt and have hello world. Thank you, Carv. Appreciate it. 0 mistakes on a live code. So you can also do this with objects. So you could write an array to the file, but the only thing is, when you open the array, because we're kind of writing binary objects and not ASCII things, we're not going to be able to see like the way that you'd print out an array. You've actually written the contents of memory to the file. And so if you open it up as a .txt, you'll see something kind of random. Now, the way you handle that is, if you want to print it, then you'd have a C program which reads back in that file, processes it, and reads it. We have a couple of questions. Okay, let's take Tim's question first, because I think he has a microphone.
I don't know if anyone else has done this, but occasionally, like, either on purpose or by accident, I'll click on the actual like program exe and like open that in text file, and it will have like this absolute gibberish. And I assume that the reason for that is it is, yeah, like exactly like that. And I guess a lot of them are not even valid characters, which is why it's kind of going crazy. But like, I assume that it is taking in what is binary that is not meant to be read as ASCII and just like forcibly reading it as ASCII, because I guess it doesn't have any way of telling that it's not meant to be ASCII.
It doesn't know that it's not an ASCII file in this case. What we could do though is modern editors like Visual Studio Code allow us to view it in a hex editor, and then we can actually see the actual values inside memory in base 16 that are inside the file. So in this case, the file starts with 7f, which in integer is 127, so that's going to be a non-printable character in ASCII. Then we get 45, which is 45 is 69, then 76, then 70, which actually does spell out 3 letters, ELF, which is intentionally in ASCII. This allows the computer to recognize that this is an ELF file by including those couple of characters at the start. But then we get all kinds of other things which don't make any sense in ASCII, which is why when we try and open it as a text file, it looks super weird. Vincent has his hand up next, and then we'll go to Gav.
Basically, my question is, what would happen if instead of, say, you did .txt, you said, I don't know, .docx on a Windows or something?
So the file extension doesn't actually matter because what you put in the file is what you put in the file regardless. However, the operating system uses the file extension as a hint to what type of program it should use to display to you what is inside the file when you double click on it. So for a TXT file, my computer is instructed to always open Visual Studio Code because that's how I like to view TXT files. For a docx file, which is a Word document, that's actually not written in ASCII. That's a kind of interesting and complicated format. And so by putting docx at the end, you tell your computer, instead of opening this in Visual Studio Code, try opening it in Microsoft Word, which knows how to handle that particular file. So it doesn't matter what you label it. Like if you right-click on the computer, you can sometimes do like open with or open as, and that just tells the computer, I want to override whatever the extension is and give this file to whatever program you choose. Garv, you had a question.
Does that mean that you can serialize any struct just by copying like whatever's in memory to like a file?
So to expand on what that question means, to serialize something is to take the data and then put it in a format that can be written to somewhere else, such as sending it out over the network or writing it to a file. Now, yes and no. If you serialize a linked list is mostly pointers. And so if you were to convert those pointers and write the value of the pointers to a file and then try and read them back, when the second time you open that file and you read in the pointers, those pointers are now to random places in memory. They're not on your heap. They're not part of anything running, and so it won't make sense. And so serialization, the art of taking a complicated data structure, writing it to a file, and then being able to bring it back and recreating the thing, is actually a little complicated in some instances. For something like an array, really easy. For more complicated data structures, that gets hard. Any more questions? Kind of happy? Another one from Tim.
Yeah, so you mentioned how in this case, at the very start, you have the ELF to let the computer know what it's meant to be. So is the file name itself somewhere in this, or is that considered like a separate bit that comes before the file itself?
The file name is not embedded in here. The file name is... it's a little complicated why we have a difference between the file name and the file type embedded in the program. Part of the reason is to abstract away the details of like running and executing a program from storing a program or storing data, because we want our manufacturers of our hard drive, the people who write the file system code that manages files, to not have to interact or not have to know the details of how a program gets executed in order to design their arrangement. You could imagine a file system which has no file names and just has things serially in order. And in fact, there are some ways of storing data that do something like that, which, older VCRs, like old cassette tapes, they don't have file names, but they've still got ways of storing data. And if you wanted to store programs on a VCR tape, you can actually do that, but there's not an inbuilt way of storing file names, and you don't want to have to link the design of your storage mechanism to the design of how you're representing your data, at least in that way. So I've included 2 sample pieces of code for you to look at just to start experimenting with. And now we will take a 5-minute break, and then we will go and actually put this all together and look at merge sort. Now I will warn you that the merge sort example we're going to look at is just going to be a simple computer merge sort in RAM, but you can use the techniques we're learning to combine it and run it in what we call external merge sort, which is split across different files and different computers. I will see you all in 5 minutes at 22 past 11. Okay, and we are back and we are ready to talk about merge sorts. So let's remember Daniel's idea that we discussed right before, which was that if we have a very large array and we want to sort it, instead of tackling the whole problem at once, what we can do is we can split it into 2 subproblems, solve the subproblems, and then join the subproblems back together. Can anyone remember earlier in semester a place where we used this kind of technique of splitting something into smaller and smaller subproblems and then eventually reassembling them? It was something from like one of the early weeks. And it was Sam. Do you have a microphone there? Convenient.
Is it similar to recursion?
Similar to recursion. What did we do when we were studying recursion? There was one problem that we used to illustrate it.
It was like was it the Tower of...
Yeah, the Towers of Hanoi problem. So if you wanted to figure out how to solve a problem with 5 disks, you would solve a problem with 4 disks, 3 disks, 2 disks, 1 disk, and we know how to solve the 1 disk and the 2 disk problems. And so this enabled us to compose those solutions to build the larger solution. Now, admittedly, that was only a single division, would be ignoring one element and then solving it on smaller elements. But the idea of merge sort is very similar, except now instead of dividing it into one piece that's smaller, we're splitting it into 2 equally sized pieces. Okay, so this is the very start. We have our array. The first step is going to be divided into 2 parts. So let's split it down the middle. And now what we're going to do is we're going to solve the same problem just on 38, 27, 43, 3, and then separately 9, 82, 10. Coming up? Yeah. But this problem is still too big for us to solve, so we're going to split each of these in 2. So we have 38, 27, 43, 3, and then 9, 82, and 10. But we still don't know how to sort 2, so let's sort 1. So 38, 27, and this is looking silly because I'm essentially writing the same thing over and over, but in the next step, it'll become clear. So now we have an individual array for each of these items. So let's focus on one of these chunks at a time. So let's look at this half of that one, of that half of that one, of that half of this one. So we have just the item 38. And now to go one level up in our recursion, what we're going to want to do is we're going to merge it with the next level up. So we're going to want to merge the result of sorting just the 38 with the result of just sorting the 27, which, as we said, there's no real sorting involved in sorting a single element. And so the way we're going to do this is let's create a new array with 2 places for each of those, and then figure out which one to put in first, from the left array or the right array. Now let's say we're going from smallest to largest. Should I pick from the left array or the right array? From the right, let's put the 27 and the 38. Okay, so now we have solved that part of the problem. And now we have to solve, which means we've solved this level, solved that one, and now we pass the result back up to here. Same thing, let's do it for these two, 43 and 3, that's just going to give us a 3 and 43. So now we do our same process again. Let's have an array for 4 items. And let's start at the smallest item from both of those. And Chi, you were nodding along with this one, so maybe we'll give you the microphone again. Okay, so we now have 2 possible arrays to choose from, and each of these have 2 elements, but let's start at the left side of both of these elements, because we know of each of these arrays, because each of the arrays themselves is sorted. So now we have a choice to make. Do we pull an element from the left array or from the right array? So here's our left array and there's our right.
Are we sorting in an ascending order?
Yeah, ascending order, so smallest item first.
Okay, so I think we should choose the right.
So we pull an item from the right one, which means we've now already looked at that. So let's move our arrow over by 1. Now should we pull from the left array or the right array?
Left.
Left array. So now we pull the 27. So I've seen the 27, and so we move our arrow over by 1. Now should we pull from the left array or the right array?
Left.
Left array, there's our 38. And now this arrow is at the end of the array. So that means we only have one choice. So we just put that 43 in there. And so now we have sorted that whole side. So let's do the same thing, and let's just do this really, really quickly. So I'm going to write it out myself. Don't know why it suddenly made my lines really thick. There we go. So that'll be 9, 10, 82. Okay, but now we've got a slightly larger challenge because we have to merge these 2 pieces. So let's do the same trick again. Let's have an arrow that points to where we're up to in both of the arrays. Let's make a new array that's big enough to fit all of them, and then put the items in one by one. So this is our left and that's our right. Which do we pull from?
From the left.
And how do you, just say out loud for us, how do you know which to choose from?
Because it's smaller.
What is smaller than what?
3 is smaller than 9.
And another way of saying that a little more explicitly is that the current item being pointed to in the left array is smaller than the current item being pointed to in the right array. And that's going to be our check each time. Which of those 2 items is smaller? So the 3 is smaller, which means we now move that little pointer along and point to the next one. And now which is smaller?
9.
9. So we move our little arrow along. Which is smaller? 10. So we move our little arrow along. Now?
38.
28. 27. You have to look where the arrow is.
And then 38.
38. Oop.
And then 43.
43. And then we've finished this array, so we don't have any choices, so we just put in all the elements that are remaining from the other one. 82. And then we're done. So merge sort is actually pretty intuitive. The only bit that's more interesting there is that process of merging them back together. The splitting is really simple, and the way the merging works is just have your 2 sorted subproblems and choose which one you're going to draw from to put as your next element in the final sorted array. Now, do we have questions on merge sort? Bowie, let's get your microphone.
How do we decide on the size of the symbol array? Like when you go down from the right,
how do you decide on the size of which array?
the assemble array? It's like you allocate 3 spaces for the 9, 10, and 80.
That one? Oh, this, I kind of skipped a step. So
Fill it up like all.
each of those are of size 1, and then I have the 9 is on its own, and then the 82 and 10. That would have become 10 and 82, and then I would have merged those.
Okay.
I just didn't want to do the exact same process all over again for the right side.
Okay.
Clear enough? Other questions on merge sort? Okay. So the code for merge sort is also delightfully simple. And this is pretty much it in pseudocode. It's if you only have one item, return, because there's no sorting to be done. Otherwise, figure out the midpoint of the array, run merge sort on both sides, and then merge the sides together. Now, obviously, the trick is that the merge step was a little more complicated, and so that's where we have some of the more challenging code. And this is what the merge code looks like. But because we've been doing it by hand, we already kind of get the functionality. So the first thing to do is to copy the elements into a temporary array. So we need to have a temporary array that we're going to then use to put our items in. Set up some variables for our pointers to keep track of where we are on the left half and where we are on the right half. Remember, we were doing that thing where say, should we choose from the left half or the right half? If we chose from the left half, move the left half's pointer over 1. So those, we need a variable to keep track of those. So S1 and S2 are going to be keeping track on the left half and the right half what we're up to. And then what we want to do is we want to check which element we want to have in a loop, and until we're at the point where we have gone to the end of one of the subarrays, what we do is we iteratively check which item should be the one we insert next. And so that is our code over here. So figure out which is the larger of the two. If the larger is coming from the T array, put the T element into the new array, and increase that pointer and increase where we are in the final array. Otherwise, pick the element from the other side of A and put it in there. And at the end, we are just going to copy over all the remaining elements. And this gives us a process that diagrammatically looks more or less as follows. Now, you will have seen this if you remember the diagram from quicksort. The merge sort one looks a little different. So the way it's going to work is we're going to start with our A array and a T array. Our T array is going to have both our A and our T are going to have sorted elements in them, and our goal is to merge them together such that our final array, our final A array, has all the elements of both. So our merge step is going to work to fill in the array by choosing the correct element from each of the sorted sides. Okay, let's take a look at it on the computer. So this is very similar code to what you've seen before for our other sorting functions. We're including sort scaffold, which has our comparison function, which allows our merge sort to be polymorphic. We have a swap function and a copy function. But beautifully, let's scroll down to the merge sort itself. And the merge sort code is very, very short. So looks almost just like the pseudocode we had before. If n is smaller than or equal to 1, just return, choose the midpoint, and then do recursive merge sort on the left half and on the right half. And in this case, mid is just being used to segment the chunk. So instead of creating a whole new array for the left, creating a whole new array for the right, we're saying just in terms of what you're looking at, look at the A array, look at its left half and look at its right half for the purposes of running merge sort. And then once you have the left half and the right half each sorted, merge them back together. because remember, just because the left half is sorted and the right half is sorted doesn't mean that the whole thing is sorted, because you may have elements that really should have been in the other half in the first place. And that's what our merge is doing. Okay, now let's look at the merge function here. So it's just like our pseudocode. So first copy the left half of the array into a temporary array, because we're later going to be, we want to be sure that we're not overwriting those elements when we're copying things back in. And then as long as you are still within the bounds of the left array and the right array, check which side is bigger. Is it from the left half or the right half? If it is from, I forget which half is T. T is the left half. Yes, T is the left half. If it is an item from the left side that's bigger, copy the first item from the left side back into the final array and increment the arrow for the left side. Otherwise, copy the element from the right side to go in next and increment the arrow for the right side. Then, if there are any remaining elements because we've already reached the end of the left side, of the right side, sorry, copy all the elements back in. And now everything is in its final position. Questions on that? Okay, so let's run this one. Oh, what did I forget? Everyone, what did I forget when I was compiling it? Yep, I didn't put the name of the output. Oh. There we go. And then we see, just like we've done for our other sorts, we get our output on the number of comparisons that merge sort has performed. So one thing for you to do at home is to take merge sort and compare it with all the other sorts in terms of realistic performance. But like with any algorithm that we do in this class, we also want to, aside from the practical performance evaluation, we want to do our theoretical performance evaluation. So we want to know, in this case, how many comparisons does merge sort actually need? So let's go back to the code for merge sort very quickly here. No, not that. Code for merge sort here. And let's look at the way that we would count the number of operations. So one way to count the number of operations is to use a recursion relation, which defines the number of comparisons it takes based on the number of comparisons it takes for a smaller version of the problem. And that makes sense in this case. So however long merge sort takes, it should take twice as much as merge sort on half of the elements, plus the amount of time it takes to do the merge. So for merge sort of length n, merge sort of length n should take 2 times merge sort of n on 2, plus the total amount of time it takes to merge. Now let's think back to our merging code over here. How many comparisons are we doing? If we're merging, let's say we're merging k elements in total, how many comparisons do we have to do? K. Garv, why do we only have to do k comparisons?
Because if you go like first element of each of the first arrays, you see which one is bigger, you pick that, then you move the index later. So for each element, you're looking at that index once, like put it.
Yeah, essentially each element is getting picked only once, and there is every time there is an element that wins that comparison war. So that means in every step, we are adding 1 to the pile, and because there are only n possible items to add to the pile, we're doing a maximum, k to add to the pile, we're doing a maximum of k steps, where k is the number of elements in our final to-be-merged list. So that gives us our runtime for our merge. So our equation is going to be 2 times merge sort of n on 2 plus O of n, because merge takes O of n. So we can now define our recursion relationship, which is just what we were talking about with Garv before. So we have to do n work for a merge, and on top of the n work for the merge, we have to do 2 times the amount of work that it's going to take to run merge sort on each of those 2 halves that have been divided by 2. Now, the other thing that we can say though, is when there's only one item, merge sort only takes one step. It just has that return immediately. So if we can somehow break down this recursion relationship, so this is for n, now let's write down the recursion relationship for n on 2, now let's write it down for n on 4, now let's write it down for n on 8, and all the way until we get to 1, and sum those together, then we'll get our final runtime for merge sort. So we can essentially do that as roughly as follows. So we get a full merge plus 2 times a merge of n on 2 plus 2 times a merge of the merge sort of n on 4, which gives us that relationship over there. So let's just rearrange it slightly. So we see in each of these expressions we have an n. So let's pull the n out to the front of all of them. And then all we have to do is figure out how many times to multiply 2 by and how many times to multiply like 1 on 2. So that gives us an equation as follows. If you just work it out, you get 1 on 2 to the 0 plus 1 on 2 to the 1 plus 1 on 2 to the 2. And how many of those terms will we have? Well, we know that we can only keep dividing the array on 2 log n times. So that gives us a relationship as follows. So we take the n out the front, we take 1 on 2 out the front, and then we get log n. And what's the big O of all of this, Garv?
And look,
N log n. So we ignore the n because it's smaller than n on 2 log n, and then we ignore the 1 on 2 because with big O we just throw out the constants, and so we get merge sort is n log n in the worst case here. So here is a challenge for you to think about at home. Write merge without using this temporary array that we were always using. Mal, you got a confused look?
Oh, well, I'm just thinking that about the challenge. What about we using some, temporary space to save the elements we are, operating with?
So it's okay to have a little bit of temporary memory, but what you're trying to do is avoiding having a whole temporary array. This is a hard challenge though. So to take ourselves a bit of Moffat wisdom to compare quicksort and merge sort, we're kind of doing opposite processes with each. With quicksort, we had hard split, so figuring out how to partition was really difficult, but it was really easy to join them. You literally just line them up and put them together. For merge sort, the splitting is the easy process. We just split it down the middle, but then the joining once we've operated on them is hard. And that's kind of an interesting way to think about each of them. So another thing that we might have been, to refer back to earlier, the whole point of using merge sort was that it has some benefits that heap sort does not. So for one, we're still dealing with chunks of memory that are close together. And with the other, it's got this process that allows us to split a very large array into chunks that can then be operated on parallel, and it's just the merge operation that's going to have to be done all on one machine. Or there are ways of doing it across multiple machines, but that's probably beyond the scope of this class, but ultimately you do want to store the results generally in one place. So I'm not going to show you how to do merge sort across multiple files, but it is a straightforward extension of the code I showed in class. So are we done with sorting? What do you think? Have we learned as much about sorting as we need to? We've got BOGO sort, quantum BOGO sort, insertion sort, bubble sort, merge sort, quick sort, heap sort. Are we done with sorting?
Not yet.
No. So this is where, if you feel like it, if you've enjoyed sorting, there's a whole world of sorting research. And in fact, there is a whole lot of Wikipedia wisdom on making sorts that are even better than the ones that we've done now. So for a totally generic sort, n log n is the best bound. However, if you know some extra stuff about your data set, you can start to do a bit better. Now remember that we took a bit of a look at ternary quicksort, and we had this multi-key quicksort where we had this advantage that we knew that there were only like 26 letters in English, so we could actually do a sort that was more efficient. So the Wikipedia page on sorting algorithms has a whole nice little section on sorting algorithms that you can run if you know a bit more about your data distribution. So there's Thorup's algorithm that I don't actually know in detail, which is a sorting algorithm that if you know that the domain of the keys that you're sorting, so if you know you're only sorting numbers from 0 to 100 or 0 to 1000 and you're not allowing arbitrary items to appear in your sort, that runs in big O of n log n, which grows much, much slower than log n, and O of n space. So that's pretty good.
This is somewhat silly, but it does build off the question, it is an active field of research. I take it the question of whether or not it is possible to sort a lot of Chinese characters is also in, say, I don't know, O n log n time is also an actively researched question.
So you can do it in n log n for sure.
As in a really, really large set of Chinese characters.
Yeah, so that's generally not a solved problem, but you can use already one of these specialized algorithms. As we discussed though, your real life performance is going to be slow though because the particular parameters that you're using are bad. If you're, for like the multi-key quicksort, we had a bit of a discussion about this, where you can use multi-key quicksort on the larger set of characters, but it's going to exhibit poorer real-world performance because the constant factors, which we ignore in asymptotic analysis, actually come into play.
Right. Okay.
So from now, we're done with our discussion of sorting algorithms for the semester, I think, I'm pretty sure, which is good news because we have now managed to distribute all the Taylor Swift tickets, but we still have some open questions because now all of you are going to show up to the stadium, to the MCG, and unfortunately, Ray has lost her ticket. She knows she's in the database somewhere, but she has to ask the guard to help her find her seat just based off the QR code. So the QR code is going to say, is going to hopefully give us back, yes, there is an entry somewhere in a data structure held by the MCG that has both Ray's name and the seat that she's in. And what we want to do is we want to make this very efficient. So we need to make sure that for everyone who needs to look up their seat or look up their details in the database, they've got a very easy way where just based on their key, so the key might be their name in this case, that we can very quickly retrieve all their details, which ticket they were sold, when they were sold it, how much they paid for it, that we can retrieve that very efficiently. And we discussed this already in an earlier lecture. We had a name for this abstract data type or data structure. HashMap was an implementation of it.
Dictionary.
Dictionary, yeah, thanks, Vincent. So this is a data structure that looks something like this. We want a mapping of names to seat numbers or a mapping of any key to any value. And this is indeed our hash table. This was created, is one implementation of our abstract data structure, which is a dictionary. The reason I differentiate between dictionary and hash map or hash table is because a hash table is a way of implementing the behaviors that we want from a dictionary. Just like that we could create a priority queue using a min heap or a max heap, we can create a dictionary using a hash map or a hash table. But frequently people just talk about these as hash tables and less frequently talk about them as dictionaries because hash tables are very, by and large, the most common way to actually implement this. So this is actually the result of some industrial research in the 1950s by Jean Armdahl, whose name you'll probably see in a number of other places in computer science, Elaine McGraw, Arthur Samuel, and Hans Lund, who were all working at IBM at the time. And the core idea that's going to make this data structure work, this concrete data structure work, is to convert the key, so the name of the student, into an index in the array somehow, in a way that's consistent, such that if we get the person's name at a later time, we can then figure out again how to get it right back to that same point in the array without having to arbitrarily go through every index in the array. So if we know that we need to jump to the third index in the array, what is the runtime of like going to a specific index in the array? What's the big O runtime of hitting index 3? No? If I know that the item I want is at index 3, one step. Just like in C, remember how we access the ith index in an array? We just do like AI, and then we're all there. Now we are going to take another 5-minute break, and I will see you all back at 7 past. Welcome back, everyone. We are going to talk a bit more about dictionaries and in particular their concrete instantiation through hash tables in the next component of our lecture. Remember, the key idea here is to be able to convert keys, pun intended, into an index in our array so that we can then get O of 1 lookups, because if we know where in the array we want to go, we can go there just with one single step. So if we had our mapping of IDs to seat numbers, we could also have these as keys, and then the trick is to figure out how to convert someone's name into their ID in a consistent way, such that when they show up, when Ray Ray shows up to the MCG, she doesn't need to know the internal ID number being used for her inside the database. There is some deterministic function that converts the name into that ID, and then we can use that ID to pull out that index in the array. The way this is going to be done is unsurprisingly using something called a hash function. This is a function that's been very specially designed with a couple of properties, some of which we'll discuss, to ensure that this process is efficient for the purpose of lookups, and also when we use it in cryptography to ensure the security of the operation. But that's going to be outside our class. If you want to know more about secure hash functions, come see me for third year information security. The core property of a hash function is going to be that it's going to map a large input space into a much smaller output space. So the input space might be the set of all people's names under 50 characters, just putting a 50 character limit on it for convenience. And then the output space will be indices of an array of fixed size. So let's say our array has spot 500 people. We want it to be whatever their name is, they're always going to map into one of those 500 spots. And so the domain and range of the function are going to be according to these constraints, where the input space is much larger than the output space. What we're going to then do is for a given key A, so the name of the person, generate a value T, which is feeding in their name into the function. So you feed their name into this function, we'll call it H for hash function. It'll generate an output T, and then we will use T as the index of the array in which we're going to store their data. So let's say we feed Ray Ray into the hash function. Hopefully she comes out alive. And the result is the number 3, then we're going to store the details of her seat number at index 3 in the array. And if she then comes back to us later, we can just run this computation H of her name again. It'll give 3 again, and then we can go back to position 3 in the array. Now, some goals for our hash function to actually make this usable is that our hash function should spit out different numbers for every different person's name as far as possible. Now, obviously, it's impossible to do this perfectly because there are only 500 slots and there are tons and tons of names. So some of those names are going to end up being in the same spot. There's just no way to make it work. That's called the pigeonhole principle. But what we do want is that if we select some random names, like if we take Xia and Mal and Gav and Ray Ray and whoever else we want from our class, like let's take Jamun as well, we want with high probability that those names will end up in different places. So assuming that the data we're getting as input is relatively random, we want with high probability that they're going to be distributed across the different space, output space. So every value h of whatever, so the value y that comes out of it, should be uniformly likely, and it shouldn't depend in a way that's obvious on the input. I mean, obviously we can't really have it not depend on the input because otherwise it wouldn't need the input at all. But the idea here is that you shouldn't be able to guess where the person is going to end up. Now we have a problem because we are actually going to get these collisions. So even if we've designed the greatest hash function, we're still going to end up in instances where, let's say, Ray Ray and Gav's names did actually end up hashing to the same value T. It's a trap. So there are a few different ways that we can handle collisions, and each of these, depending on which behavior we choose, we're also going to get different sorts of runtime behaviors. And again, choosing these is going to be a mix between algorithmic analysis and real-life performance analysis. So for handling collisions, these are our 3 strategies that we could possibly do. So strategy 1 If you hash the item and you see that it would take you to a place that's already occupied by something else, have a second hash function handy that behaves a bit differently, and then use that second hash function. We still need a way, and we'll talk about this in a minute, to figure out for a given person, should I use the first hash function or the second hash function? But we do have ways of resolving this. And then if you get a collision on the second hash function, well, maybe you have a third hash function. This is called perfect hashing, which is essentially do a better job of hashing or use a second or third hash function to resolve the conflicts. Then we have open addressing, which is if you were meant to insert them at location 7 and there's already something at location 7, well, maybe try location 8, and so on and so forth. And then our last strategy is what we call closed addressing, which is store everything that was meant to be at location 7, but have some data structure there that allows you to store multiple things at the one location in that array. So let's look at strategy 1, which is chained hashing, which is to use a second hash function if you get a collision. So here we have a few, so what we're going to do now is we'll do a few demos of inserting things into our hash table. We'll make up some values, some outcomes for the hash function, and we will see how to resolve the collisions. So in this case, let's take a person Chen and feed them into our hash function. They produce a value 1. So we want to insert their score, 83, into location 1 in our hash map, into our hash table. Now Ella comes along and has a different score, 99. Ella's not here today, sadly. Ella has a different score, 99, but also hashes that same 1. So what do? Well, in chained hashing, we're going to have a second hash function available. And so when we run our second hash function, we get a value of 4. And so we're going to store Ella at 4. But now we run into a problem because when we want to get Ella back, we're not sure if we hash Ella with the first hash function, we look up in our table, we get 83, which was not her score, and we wanted to get 99. So the question is, how do we resolve this? And let's take someone from all the way in the back. Who's got a microphone? So let's say that we hash Ella and with hash function 1, and it takes us to location 1, and we get a collision, and now we don't know whether her score is 83 or whether it should have been 99 from the second hash function. Is there additional data that we could store in our hash table that would allow us to distinguish which of these two cases we're in?
It's like there's something that stores the key of like each name, like either correspond to 4 or something.
Give me a bit more. You were totally right. Give me a bit more of that. Explain it just a second time.
Is it like making new dictionary to tell like who is correspond to which key?
So one way to do it would be to have a second dictionary, and then when we look up index 1 in the second dictionary, it'll say who that was meant to be for, and if it's for the wrong person, then we use the second hash function. But there's another way we could do it. We could do it with just one hash table. How would we modify our hash table so that we could do it with just one? It's the same idea, it's just a slight modification. So we needed to store an extra piece of information, right? We needed to store the person's name. So how could we modify our hash table to store both their name and their score at that location? In C, how would we do that? Store two pieces of data that are linked together in one item. Yeah, we could use a struct. So while a struct is the C version of this, the idea is the same. If you store the key and the value at every location, you still have the index being corresponding to the hash of the key. But if at every location you're also storing what key it's meant to be for, then you can do one lookup. It's the same idea as having two dictionaries where one stores for every index tells you who was meant to be there, and the other one stores the data associated with them. But here we're just joining them together into one object. And that actually solves the problem entirely, just at the cost of storing additional data at every slot in the hash table. The expected runtime of this is going to be O of 1 plus alpha. And alpha is going to be a factor which tells us how full the hash table is. And the reason this alpha appears is because as the hash table gets more full, your chance of colliding with something else goes up. So the amount of time that it's going to take you to look up is going to go up because you might have to use your second hash function or your third hash function, etc. So alpha is going to be the number of times we have to use a new hash function here. Now, this is also kind of interesting because traditionally when hash tables are taught, they ignore the fact that the hash table could become kind of full and you'll run into this issue. So you're getting a preview of things that might be taught at master's level here, which is, I think, kind of cool. So we get O of 1 plus alpha, which mostly people are going to assume that there's not very much in the hash table, so they'll write it as O of 1. We already talked about that. So for the same thing with deletion, the way deletion is going to work is because we've got multiple hash functions, we're going to need to know whether to delete the item stored at hash function 1 of the value or hash function 2, and we get around that by just storing the key at the destination along with the value. Garv has a question. Ray, you've got the mic.
With this strategy of like using more hash functions, and every time you have like a failure of like putting it in, you have to go to like a new hash function. Doesn't that mean that if you're like using 500 names, then you would have to have 500 hash functions?
No, because the goal of the hash function is to give, if you put a different name in there, it should give you a different value. This was just an example of a bad hash function which mapped the first two people I tried to the same location. Okay, so that's strategy 1, have multiple hash functions. Okay, strategy 2 was letting items leak past the location in which they were meant to be. So if it was meant to be at location 2, maybe you push it along to be at location 3 if location 3 is empty. If location 3 is full, push it along to location 4. If location 4 is full, push it along to location 5. So here is an example where I want to insert Chen again. Chen maps to 1, and so we can just put that in. But now Ella comes along and also maps to 1. We have a collision, but instead of using a second hash function, now we're going to go consecutively along through our hash table and try and find the first free location for her. So can she go in location 2? No, U is already there. Can't go to location 3, V is there. 4 and 5 are also full, which means that the first free spot that we're going to get to, allowing ourselves to wrap around, is back at location 0. There was an initial formal analysis of this performed in 1962. The expected cost of the lookup is, as written there, 1 plus 1 divided by 1 minus alpha, with an expected cost of, I think that was meant to be insertion, of O of 1 plus 1 minus alpha, 1 on 1 minus alpha squared. That's a bit hard to say. But the actual behavior of this in practice is mostly going to be O of 1. It just gets worse as you add more items. Now, but in practice, we are going to get O of 1 runtime. So again, not much to worry about. And in actual practice, we do assume that implementations are O of 1. So for this open addressing scheme, for linear probing, that's the name of the scheme that we're looking at, deletion is going to work similarly to the way before, where we now need to store both the key and the value at every location in order to correctly perform deletion. So let's say that we want to delete Kevin. So we can look up Kevin in the hash table, his value is 4, but now instead of leaving the slot blank, we're going to put what we call a tombstone there. And the reason we need to put the tombstone there is because if we look up Ella, we now need to know that we should still be going along, and hitting a blank space doesn't mean that Ella isn't in there entirely. So if we look up Ella, we go along, U, V, now we hit the tombstone, and the tombstone says, well, there used to be something here, so it's possible that Ella is just further along. So that allows us to go past, and then find Ella, and now we can mark her with a tombstone. Okay, that's our strategy 2. And now strategy 3 is called separate chaining. And this is the idea where not using multiple different hash functions, we're not letting things leak. Instead, just store everything at the location that they're meant to be and use a data structure to store multiple things there at once. So let's start with Chen again. We're going to store Chen at position 1. And now we get a collision with Ella. But instead of pushing Ella out along, what we're going to do is we'll have a linked list at that location, and we will just add Ella to the linked list when she comes along. Now we're going to add Journey. Journey is at location 4. And when we look up Ella again, now we just are going to iterate through the linked list to find the correct item. So now if we want to delete Chen, first we have to do the hash table lookup. And now we do the deletion. And this is also an indication of why we might choose to use a linked list rather than an array there or something else. And then our last strategy, number 4, is something that's a bit more interesting altogether, called Cuckoo hashing. Who knows why cuckoo birds are a bit scary? Tim?
They will go to another bird's nest, kick out the eggs already in the nest, and then lay their own eggs in the other bird's nest.
Yeah, so cuckoos are vicious. They hostile take over other cuckoo birds or other birds altogether and take over their nests. So that is the essential idea behind cuckoo hashing here, is when you get a new item that's coming in, what we're going to do is we're going to kick out the previous item that was there. And the way this works is as follows. So have 2 hash functions. So step 1 is use your first hash function and check if there's a free spot at that location. If there's a free spot, great. If you get a collision, kick out that item from the collision and move it to a new location based on your second hash function. Then if there's a collision there, kick out that item and do the same process again until you get a point at which every item is safely in the hash table. However, I'm sure Gav was about to ask this question. I could see it on his face, actually. It's like, what if you get a cycle? What if you kick out one thing and that one thing kicks out another thing and then that kicks out the first thing again? Was that going through your mind? I could see it there. So if that happens, essentially what you have to do is you have to rehash the entire table, and there are some strategies for redoing this such that you try and get everything in place. In reality, when you do this, it's generally fairly effective. So despite the fact that you might worry about this rehashing process, on an amortized basis, which means accounting for the total cost of doing this process divided off over how many times you do it in total across all your insertions and deletions, it ends up being efficient. So then we get a nice table as follows for all of our different strategies. So I've left off the just having better hash functions on here. We get the worst case for naive chaining, which is just adding things all at the same location. We get a worst case insertion of O of n, because what happens if our hash function mysteriously mapped everything to the same location? Then in theory, you could get an O of n lookup. In reality, that doesn't actually happen, but at least that illustrates why our algorithmic analysis might be a bit different from our real-world performance in this case. And then you can follow it through for all of our different strategies. I'm not going to go through the details of the table, but the vast majority of these entries are O of 1. And so in practice, when we talk about hash tables, we say they have O of 1 insertion and O of 1 deletion, because we assume that we're going to use the hash tables in a fashion where we're not overfilling them, such that we get 499 elements and trying to put in the 500th. A better strategy then is just to copy the items over and make a much larger hash table. So for linear probing and cuckoo hashing, the reason why we often choose not to use them is because you need lots of hash functions that are relatively independent in their behavior, and that gets a little complicated and makes the design much trickier. So one thing about this whole process, and as we just said, you actually need to have good hash functions for this really to work at all. If your hash function is going to map everything to the same place, then you may as well not be using a hash table. So there are a few things that we can do, or that we're going to aim for with our hash functions to make them good. So these are a few just high-level pointers. We want to use for a given person's name, we don't only want to use some of the data in their name, we want to ensure that every letter is used or every bit is used. And the reason we want to do this is because otherwise, let's say we have Garv and Gar, G-A-R-V and G-A, who both want to be inserted into the hash table. If our hash function only relies on the first two letters of someone's name, then they're automatically going to get a collision. So you want to be sure that all the data gets used. You also want to check the distribution of the real data to try and find a hash function that's going to behave well on your real data. Again, with all the results that I've talked about thus far, the big caveat is that they're only going to apply when the table, a lot of the results that I've shown you are only going to apply when the load factor is relatively low. If the load factor gets very high, you start to get interesting sorts of behaviors, and this is still an area of active research. Vincent, did you still have a question?
So for the previous slide, I was going to ask, let's say you have the very unlikely case where, say, because one of the things the carrot was check on real data. What if, say, for example, in the admittedly very unlikely case of this is the first time anyone has done a hash function on the set of data that you're using?
So there are hash functions that work very well on generic data, but if your data is weird, then you're going to want to think carefully about it. For the most part, we do have things like cryptographic hash functions that work well for arbitrary input and give us good behavior on them.
Okay, so not really a huge problem.
This is just saying like the things that you want to have when you're designing it in mind, but we're now at the point where we have designed them. Now,
could we just say that for hash functions, they're kind of like a mathematical nature is to transform the uniform and non-uniform data into a uniform distribution?
Yeah, or as close as possible. Ultimately, we're not actually going to be able to get a uniform distribution because that would make the hash function really, really complicated to the point where the size of the hash function is as large as the size of the data. But we try and get as close as we can. So in practice, the way we're going to avoid a lot of the pathologies with hash tables is just by resizing the table whenever the table gets too overloaded. And for example, in a real programming language, Java has built-in hash tables and will automatically do the resizing for you if the hash table gets above 75% full. Another thing that we might see is like Cuckoo hashing allowed us to get around some of the annoying stuff with the linear chaining and with the open addressing by just distributing the data well across the entire table. But unfortunately, in practice, it ends up being slow for the same reason that we talked about earlier, why heap sort is slow. Because Cuckoo hashing is going to have multiple references to parts of the table that are very far away from each other for an insertion, this ends up taking more time in practice than it is just going to be to use something like open addressing, which is a kind of an interesting result where the big O analysis is again going to diverge from the use of the algorithm in practice. So there are also lots and lots of very fancy improvements for all of these different methodologies, and I'll leave one for you that you might be able to do just with what you've learned today, is a way to improve separate chaining. And with that, we're actually ready to take a look at some of the code for hashing. So you are not expected to use hashing in any of your assignments or any of the remaining work in the class. It's more here for you, again, to understand the stuff conceptually. So let's start by looking at hashingbad.c, which, there we go. Always mess that up. Need like what they call a confidence monitor where you can see over here what's going on back there. So this is an example of a bad hash function that we're using to distribute the data. So let me go over here, and here is the hash function that we're using. And what we're doing here is we're iterating over the hash function consecutively, and at each point we are multiplying the index at which the key appeared in the word by the key itself. So like, let's say A is in position 1 and A converts to I don't know, 65, so that'd be 65 by 1. If B, and then add that to, let's say the next letter in our string is B, it'd be B by 2. So it'd be 65 by 1, 66 by 2. Now, let's do it with a slightly different example, but this will still illustrate the same thing. Let's say instead of taking using the string AB, let's say we're hashing numbers. Okay, so we have a value of 14, and now the question is, can you come up with another sequence of digits that sum to 14 using the same sort of technique? So let's try it with 2, 6. So 1 by 2 plus 2 by 6. So that gets us to 14 again. So that would be the number just 26. And so the problem here is that it is too easy for us within a relatively small space to generate collisions. So this is an example of a bad hash function that's going to generate collisions pretty rapidly. So let's see what happens when we actually run hashing bad. There we go. Now let's run hashing bad. And it also needs some word input. So let's take the first 1,000 from War and Peace. Lecture 1. So I'm going to run hashing bad with War and Peace 1000. Okay, so processed 170 words, 116 distinct, required 57 string compares, so only 0.34 per word, and then the minimum bucket was 0, and the maximum bucket was 2, and we only had 1 collision here. Now let's try it with a slightly larger data set. So let's do it with, just for comparison to see how this works out. Oh. And now bucket 1617 has a whole lot of words that have actually ended up in that location. So this is ideally not what we want to see. So now let's run it with, let's use a better hash function. So I have my normal hashing.c. And now I have a hash function that is built around our prime number code from earlier. I'm not going to go into that too much more now, but let's just give it a try. And run it. And now we can see that there are actually far fewer collisions because our hash function is considerably better. And this just illustrates the need for choosing good hash functions to ensure that you actually get that O of 1 hash table behavior. And with that, class is actually over. Thank you very much, everyone.